I think we left off talking about this slide. So remember, we have our micelles, and they're going to be the emulsified ones with the bile acids. They're going to be transported into the enterocyte, into the ER. Then they're going to be reprocessed into individual cholesterol ester molecules, triacylglycerols, and then packaged up with big proteins like that ApoB48, and then exocytosed into the lymph system in the chylomicron form. So when I say the chylomicron, it's important that you can get a feel for how big this actually is. So the diameter down here is in nanometers, so it's bigger than 1,000 nanometers in diameter. And as you go from the chylomicrons down to the HDLs, what's actually the physical property that's different? What's your property that's different? Density, right, so the density is different. So we talked about the fact that this density value was a ratio, and it was a ratio of protein to lipid. So when you have a very low density, like something like a chylomicron, and this one says chylomicrons are about 0.95, I think units are grams per milliliter. So that's a relatively low density. So which means which of these two is going to have the biggest component, the protein or the lipid portion? The lipid. Right, so that means there's a huge amount of lipid and only a small amount of protein. So when we look at these chylomicrons, so remember, if we could draw in some of the components, we would have our ApoB48, we would have triacylglycerols, cholesterol esters, and then we had a couple of those little ApoA, I think it was 1V or something, ApoA1V. So the tally up of all of these proteins is very small compared to all the triacylglycerols and the cholesterol esters that are in there. And physiologically, your influence changes based on these density values. So the chylomicron is just for the lymph system. And its circulation is limited to the lymph system, goes to the adipose tissue, and then starts to fall apart. So we have other things in here. So VLDLs, IDLs, which is intermediate density lipoproteins. Then we have the LDLs and the HDLs. And so what's the current philosophy on your HDL and LDL levels? Yes? That's okay. So which one is supposed to be more? Right. And the new philosophy is HDLs as high as possible, no matter what your total, quote, cholesterol level is. So you can have a cholesterol level of 208. And if you stopped right there, they would start diagnosing you with cholesterol-lowering drugs, etc., etc. But that, it means nothing. So then you have to do your differential on it. And so when you look individually, I'm going to make you do some math here. So say your HDL is 125, and your LDL is only, what is that, 33? Did I do the math right? Did I do it right? No, I didn't. 73. 73. Okay. 83? 83. Okay, all right. Oh, I didn't get the 3 part. All right, so now you look and see your ratio of HDL is really nice and high. And so by looking at these two ratios, you can say this person does not need cholesterol-lowering drugs because their HDL is nice and high. And they were saying, oh, you know, you should have adequate HDL levels, but as long as your LDL were not too high, it was okay. But that's not the philosophy anymore. The philosophy is get that HDL to be as high as possible. Okay, so we'll do a quick little one about why, and then later on when we do lipogenesis, we'll talk about it again. So tell me about the ratio of HDL versus LDL. What's the ratios for protein and lipid?
HDL has a lot more protein.
Right, so the HDL has a lot more protein than the LDL does. So chronologically, it's this first in the circulation and then that. So how do you go from HDL to LDL?
By gaining lipid?
Yes, exactly. So you're going to gain lipid. So there's not going to be very much difference in the protein. So you can exchange out some proteins, but typically they're going to be exchanged one for one. But if you gain lipid, you're going to be able to turn from an HDL to an LDL. Well, cool. What lipid should you be gaining? Nope, no tags. But it is up there. That same chylomicron. Right, the cholesterol esters, right. So why would you want to be able to collect cholesterol esters? What did we say happens to those cholesterol esters if we let them go in the bloodstream? They are completely hydrophobic. What was the few sentences after that? What condition happens if they start to accumulate? Yeah. Right, so atherosclerosis, right? So those cholesterol esters that can lead to atherosclerosis, if you have high levels of HDL, you'll be able to scavenge those up before they create hardening of the arteries. So the philosophy of keeping these as high as possible means that over time you can collect these cholesterol esters out of the bloodstream before they become part of those plaques and the hardening of the arteries. And then you convert it to an LDL by accumulating more of the denominator, basically. And then this goes back to the liver and gets recirculated and repackaged up and excreted or used as necessary.
How do you get more HDL?
Ooh, that's a good question. Can you can speculate? I'll start writing it down and then I'll write a grant for it. Because there's people who are naturally have high HDLs. So some of it is what you genetically have. But there's a lot of philosophy that say if you change your diet in a certain way, this way you can encourage HDLs or reduce LDLs. So one of the philosophy was, well, if I just reduce my LDLs, that will be good enough. but they've started to say that's not good enough. So, but we can speculate. Okay, so this gives you a feel for, at this stage, we're transporting all those triacylglycerols, but the container of our triacylglycerols is enormous. And so we're going to be able to see how that will process down to smaller and smaller containers as we go through. And so this truly is a difference in the density. You can spin these out, and these will settle to the bottom, and those will be on the top. So you really can do an actual, you can do a centrifuge density gradient, you can do a sucrose gradient, whatever, and you can see what where those densities show up in if you start off with a mixture of densities. Okay, so we've done most of this on this slide now. So we've gotten all of it converted into chylomicrons, and we've gotten to the point where they're gone to the adipose tissue, and our fatty acids are being taken up by our adipose tissue, and our fatty acids can be transported over to the striated muscle and our heart. But about 90% of these bile acids that get produced from the liver will be recycled. So you'd have to eat a whole lot of cholesterol if you could excrete all of those. And darn, I forgot. I was going to go look up those wow chips.
I did in class this week.
And what did you find?
It was just like saying why did you even do this kind of thing. They're like not sold. What did it go in captions? It was captions like, for the like articles about them were really funny. It was like these tips will keep you sending to or keep you going to the because I wanted to see it.
Because I mean, I ate them. They just looked like regular chips, and they kind of tasted a lot like the baked Lays they have now, kind of like that consistency. But the rest of it was not anything like regular potato chips. Okay, so we've done all this, so we've got it so that we have our chylomicrons into our lymph system. So we need to start doing our lipolysis. So it's already been a lecture and a half, and we haven't even done any breakdown of it yet. So we've just been transporting it around to places that it needs to go. So we already know that when we need lipolysis, obviously, during fasting, so typically, metabolic fasting is when you haven't eaten for 2 days. So that's about what they call fasting. So fasting is not, it's been 6 hours since I had food. So we're going to see lipolysis during vigorous exercise, which is totally awesome, good for your heart. And the last one, in response to stress.
I feel like it doesn't happen for me when I'm stressed.
Metabolically it does, but you may not see a big dramatic effect.
So I just need to stop stress eating. I think that's the problem.
Oh, right. So it's trying to counteract what you're doing, and then it goes, yeah, but I'm stressed, so I need to eat. Well, it's doing this and this, so it has to, your body's going to go like, hey, let's replenish that, like with some Haagen-Dazs or something. Okay, so I wrote this two different slides. So let's do the fed state first. So we did the part about getting them into the bloodstream in the form of chylomicrons, the very, very low density lipoproteins. And so we did this part where they're going to the adipose tissue. So we'll talk a little bit about that today. So they're going to go to the adipose tissue, and then our triacylglycerols are going to be broken down and collect some fatty acids. And our fatty acids can also go to our muscles. So you did this way, we did that one, and that one. But we didn't do this part yet. So we'll come back to this slide because this one will be important because it'll connect with this adipose tissue. So under fed conditions, make your chylomicrons, go transport them to your adipose tissue, start storing, because you don't really need that anymore. And then any of this glucose that came from eating food can also go to make triacylglycerols, and then they can be dumped into the bloodstream, and then they can go to adipose tissue. So carbohydrates, fats, easy in the fed state, tend to funnel their way into that adipose tissue. And at the same time, you can also be making glycogen and things like that in the liver too. But for storage purposes, glucose comes to the bloodstream, glucose turns into triacylglycerols to the bloodstream, out to adipose tissue. Dietary triacylglycerols to the bloodstream, back out to the adipose tissue. So the only thing that's drawing out of this is energy for your muscles. So this is really the only thing during the fed state that's actually removing any calories at all from that, dumping it all as adipose tissue. Okay, so when we go, what's going to be different when we go to the fasted state? So first of all, we have a new organ in the picture.
So you're still going to the muscle, but you're pulling from the adipose and putting it to the brain and into the liver.
Exactly. So now we have adipose tissue breaking down into fatty acids that can be dumped in that fatty acid albumin complexes. And then once it's there, it can go to the muscles. But this is not going to go here. So these ketone bodies that get used by your brain can only come from the liver. So your brain can use ketone bodies and it can use glucose. But this is the fasted state. So we're assuming all the temporary glucose is gone, the glycogen is gone. And now you're doing breakdown of fat to get your source of energy. So you're breaking down your fatty acids. You can send your fatty acids into the bloodstream with your albumin. You can send them to the liver to be synthesized into fatty acids and ketone bodies, and then off to the brain. So remember, brain's not going to do any gluconeogenesis. It relies on the liver to do that. So the other part, once you break down your triacylglycerol, you get the glycerol backbone. So glycerol can be transported to the liver, and it actually becomes dihydroxyacetone phosphate. And then you can do gluconeogenesis and synthesize glucose from it. So triacylglycerol is a really awesome source of calories. And so today we're going to do a little bit about how the beta oxidation process and about the energy that you can get out of that fatty acid. So your muscles can do these reactions, can do beta oxidation. and your the glycerol that comes from the backbone can be sent to the liver, generates ketone bodies, and then indirectly goes to your brain. So there's no direct connection from adipose tissue directly to your brain. So it relies on going through the liver and then the liver back to the brain. So we haven't really talked very much about ketone bodies, but ketone bodies are the compounds like dihydroxyacetone phosphate and acetoacetate are common ketone bodies. And so you know when people are going or have that uncontrolled glucose level because they smell like acetone. So they're doing this fat breakdown because they cannot use glucose. So the glucose is staying in their bloodstream, and instead of being transported to the cell, being used for energy, it's almost like somebody who has uncontrolled diabetes is like this. There's no glucose because the glucose is staying in the bloodstream and it's freaking out. So because I have to get energy from somewhere, so they do this reaction. So they do this and they decrease the adipose tissue, convert it to glycerol, and then this glycerol produces these ketone bodies. Well, acetone is volatile, so they'll breathe it out and they'll just smell like acetone.
So somebody who fasts for 2 days, would they smell like that?
Some of them do. Especially if they're doing that plus adding a whole bunch of vigorous exercise along with that. People who have eating disorders smell like acetone because they are they're reducing the amount of food that they eat, and vigorous exercise does this, which is awesome. But without any other food, you're going to start smelling like ketone. And I go to an endocrinologist, and his office says no perfume. So he can smell.
Wow.
Yep, he wants to smell.
How strong is it? Pretty soon, like it's very obvious.
So like you know how you after a game and you sit next to somebody on the bus who hasn't taken a shower yet, like overwhelmingly powerful. And even if they took a shower, it wouldn't do any good because it's seeping out of their skin and their what's your armpit cells called? Apocrine, your honor, whatever. But that's a histology long time ago. So we're going to do this enzyme is hormone-sensitive lipase. So this enzyme is the one that's going to do that conversion from the triacylglycerols to the fatty acids. So you can imagine, is this going to be allowed to run amok? We're going to allow hormone-sensitive lipase to just start like breaking down triacylglycerols whenever it feels like? No, of course not. So we're going to control this adipose tissue release of the fatty acids and the glycerol. We'll see how are we going to control it. Let's name 2 important ways to control it. What one do you think will activate it? Think big hormone. I want to activate it though. Glucagon, right. So why will glucagon do this?
Because you need glucose.
Right. Because glucagon is the trigger for low levels of glucose. Please provide some other form of energy in the form of triacylglycerol breakdown beta oxidation. And so the inhibitory one is insulin. So I think that's on the next slide, the next couple slides. I have a little hormone receptor adipose tissue that the adipocyte that we talked about. Yeah, so later on we'll talk about this slide, which has that on there. Okay, so our lipolysis is going to be controlled by glucagon and epinephrine. Both of them are going to be hormone triggers for hormone-sensitive lipase, and it's abbreviated HSL, and there's all kinds of HSL 1 through 9 and all that stuff. But basically, hormone-sensitive lipase is what's present in adipose tissue that will break down triacylglycerols. So in the past, how have we seen hormones influence other things? What mechanism have we seen in the past? Like when we did the GLUT4 receptor. So what kind of cascade have we seen? Right, so secondary messenger system does what? What have been some of the influences of that second messenger system? So, specifically chemically, what has happened? No?
But there's phosphorylation.
Yes, the kinase is right. So phosphorylation is very common, and we're going to see it again. So we're going to see phosphorylation as a way for glucagon to influence that hormone-sensitive lipase. So again, we're going to see that theme again. So our triacylglycerols will be broken down into diacylglycerols and free fatty acids. And those free fatty acids will be able to be exported from the adipose tissue and back into the bloodstream with albumin. And hormone-sensitive lipase also does cholesterol esters. So it can break it up into cholesterol and a free fatty acid. So hormone-sensitive lipase is very active in the presence of a lipid-water interface. So why would it do that? No, you're right.
It's because it has to like bundle up to like hide the hydrophobic.
Right, exactly. So those triacylglycerols want to be hidden away. They're going to be in that fat droplet. But the hormone-sensitive lipase is going to be water soluble. So this hormone-sensitive lipase has an affinity for the interface between water and lipid. And that's the perfect place for it to have its substrate of triacylglycerols there to do the hydrolysis. So the best connection, so the hormone-sensitive lipase is water soluble. So the conditions where it can come across its substrate is going to be triacylglycerol. So it has to be able to have an affinity for the conditions of partially water soluble, partially lipid soluble, because if it doesn't, that hormone sensitive lipase is not going to be able to come in contact with that triacylglycerol. Just for the same reason, we had to emulsify all of those dietary fats to begin with. So here's a little generic hormone receptor. And so this hormone is going to start a secondary messenger cascade. And the other picture has some of the adenylate cyclase and stuff that it's in there. And in the process, it's going to phosphorylate this. So there are 4 phosphate groups on hormone-sensitive lipase that makes it in the active form. And the second messenger system is what is going to do that cascade. So depending on which hormone is on the surface, you can get that second messenger cascade to take off those phosphate groups, or you can have them have the phosphate groups be on. Let me think for a second. Yeah, active is with the phosphate groups. Okay. So the amino acids, I guess, phosphorylated. There's 2 serines and 2 histidines that get phosphorylated.
Is it inactive even if it has 3 phosphate?
Yes, so it is very sensitive to the fact that you need four of them on. And it is, from the pictures that I've seen, this is not a bad depiction because the phosphate group is actually part of the chemistry that's going on in the triacylglycerol hydrolysis. So our triacylglycerol in the presence of our hormone-sensitive lipase will be converted into fatty acids, and then the fatty acids will become acyl-CoA and ATP. So that will be all part of our beta oxidation reactions. And we'll also be able to make acetyl-CoA if we need to. So the beta oxidation step will be the next set of reactions that we need to do. So at this point, we can look at our big picture. So we have our hormone receptor. This is part of our second messenger system with the adenylate cyclase. And here is our hormone-sensitive lipase. So in the active form, it's got all of its phosphate groups on it. And it will be able to take our triacylglycerols, convert them into di and mono and individual glycerol. And then when it's in the inactive form, those same things that put the phosphate group on, we'll go take them back off again. So things that need phosphate, that encourage phosphorylation, encourages the phosphorylation of that hormone-sensitive lipase. So once we're glycerol, we can export our glycerol, and it will go to the liver, and it will go to become a component of gluconeogenesis, which is dihydroxyacetone phosphate. And then what should we do with our fatty acids? What did we see there in the past in the other slides? What were they doing once we were a fatty acid? Nope, so we broke it down right now. Now it's individual fatty acids. Now what can I do with it? Right there. Right, so now I can make it bind to the albumin and send it back to the bloodstream to be used for your muscles or your heart. So as I have these 3 fatty acids, they can be exported and combined with albumin and dumped back into the bloodstream, and then it can go to your muscles and your heart. So here is the connection between the glycerol that gets produced in adipocytes and glucose. So glycerol will be dumped into the bloodstream. It doesn't need a carrier. It's perfectly fine for it to be by itself. But it gets shunted back to the liver, and it's converted into dihydroxyacetone phosphate. And then we recognize that component of gluconeogenesis, and we can synthesize glucose from that.